Good morning, everyone. I'm excited to welcome you all today. Thank you for being here. Today, we'll be exploring the power transformer testing complete procedure. I'm Varun Vijay from the electrical department, and I'll be guiding you through this presentation. In the next few minutes, we'll cover the key steps involved in testing power transformers, including methods, safety precautions, and important parameters. So, let's get started and dive into the details of this essential process. Let's talk about the insulation resistance test, or IR test, which is crucial for checking the health of transformer insulation. The main purpose here is to ensure that the insulation is in good condition, preventing potential faults or failures. To perform this test, we typically use a device called a megger, which operates at voltages between 1 kV and 5 kV now. The procedure begins by disconnecting the transformer from the system, ensuring safety and accuracy. Then, we test between different points, the high voltage side and the low voltage side, the high voltage side and the earth, and the low voltage side and the earth. It's important to note the reading after 1 minute of testing, as this gives us a stable value to assess. Ideally, for systems operating at 11 kV, we look for a resistance of 100 megohms or more. For 33 kV systems, the ideal value increases to 200 megohms or more. These readings help us determine if the insulation is healthy or if there's a risk of failure, making this test a vital part of transformer maintenance and overall system reliability. Let's talk about the polarization index, or pi test, which is a crucial method for detecting insulation moisture. The main purpose here is to identify if moisture has seeped into the insulation, which can be a significant issue for equipment reliability. To perform this test, we use a device called a megger, which helps us measure insulation resistance. The procedure involves taking 2 readings of the insulation resistance, one after 1 minute and another after 10 minutes. These readings help us calculate the pi by dividing the 10-minute resistance reading by the 1-minute reading. Now, the ideal value for a healthy insulation system is a pi of 2 or greater, which indicates excellent condition. If the pi falls between 1.5 and 2, it suggests the insulation is in good shape, but we should still keep an eye on it. Connecting this to our overall theme, this test is vital for preventive maintenance. It helps us catch potential issues early, ensuring the longevity and reliability of our electrical equipment. Let's talk about the turns ratio test, or TTR test, which is also known as he transformat enus, he turns enus, he dacia enus, he tace enus in Hindi. The main purpose of this test is to verify the voltage ratio of the transformer, ensuring that it matches its rated specifications. To perform this test, we use a TTR meter, which is specifically designed for this purpose. The procedure is quite straightforward. First, we connect both the high voltage and low voltage windings to the meter. Next, we apply the test voltage carefully, making sure not to exceed safe limits. Finally, we compare the readings we get from the meter to the rated ratio of the transformer. It's important to remember that the ideal value for this test is within plus or minus 0.5% of the rated ratio. Maintaining this accuracy helps us confirm that the transformer is functioning correctly and efficiently. This test is a crucial part of transformer testing because it helps us verify the voltage transformation ratio, which directly impacts the performance and safety of the transformer in the overall electrical system. Let's talk about the winding resistance test, or he vidig enus, he taces enus, he tace enus in Hindi. The main purpose of this test is to detect any issues or defects in the winding or tap changer of a transformer. It's a crucial diagnostic step to ensure the equipment is operating properly. For this test, we use a DC resistance tester. This device helps us measure the resistance of each winding accurately. The procedure is straightforward. First, we apply a direct current or DC current to the winding. Then, we measure the resistance for each phase individually. Now, why is this important? Well, by comparing the resistance values across phases, we can identify any irregularities. Ideally, the phase difference in resistance should be less than or equal to 2%. Any significant deviation from this indicates potential problems, like winding damage or tap changer faults. So remember, keeping the phase difference within this limit helps us confirm the winding's health and overall transformer integrity. This test is an essential part of preventive maintenance, helping us catch issues early before they escalate into major failures. Let's talk about the vector group test, or he baked it anus, he tup anus, he taste anus in Hindi. The main purpose of this test is to verify the phase displacement between the transformer's primary and secondary windings. This helps us ensure that the transformer is wired correctly and functioning as intended. For this test, we typically use a phase angle meter or a TTR kit. These are essential tools that help us measure the phase difference accurately. Now, what should the ideal result look like? Essentially, the measured vector group should match the nameplate information. For example, if the transformer is rated as dyne 11, then our test results should confirm that the phase displacement corresponds to that vector group. This test is crucial because it verifies the correct wiring and phase relationship, which directly impacts the transformer's performance and safety in the system. Remember, accurate phase displacement ensures proper operation and helps prevent potential issues down the line. Let's talk about the no-load test, or he na inus, he lod inus, he ace inus. The main purpose of this test is to measure the core losses in the transformer. To do this, we use some basic equipment such as a wattmeter, an ammeter, and a voltmeter. The procedure involves applying the rated voltage to the low voltage side of the transformer while keeping the high voltage side open. This way, we ensure that only the core losses are being measured, without any load current affecting the results. Ideally, the no-load current should be between 1 and 3% of the rated current. This small current indicates the magnetizing current required to establish the magnetic flux in the core. Understanding this helps us assess the efficiency of the transformer and identify any correlated issues. So, this test is a fundamental part of transformer testing, giving us insight into the core's behavior under no-load conditions. Let's talk about the short circuit test, or he shod nus, he sudke nus, he dace nus. The main purpose of this test is to measure the copper losses and the impedance of the transformer. It helps us understand how the transformer behaves under short-circuit conditions, which is crucial for assessing its efficiency and performance. Now, for the equipment you'll need. A variable AC source that allows us to adjust the voltage, along with an ammeter to measure current, a voltmeter for voltage readings, and a wattmeter to measure power consumption. These instruments are essential for accurate measurements during the test. Regarding the procedure, we start by shorting the low-voltage side, meaning we connect it directly to the secondary, effectively creating a short circuit. Then, we gradually apply voltage until the rated current flows through the transformer. This way, we simulate the conditions under which the transformer operates when fully loaded. The ideal value we're aiming for is the percentage impedance, or %Z, which should be close to the value specified on the nameplate, typically within plus or minus 10%. This percentage impedance gives us insight into the transformer's reactance and how it limits short-circuit currents. Overall, this test is vital because it provides us with key parameters that influence the transformer's operation and safety. Understanding these values helps in designing protective devices and ensuring the transformer performs reliably in the field. Let's talk about the oil BDV test, or he oil anus, he BDV anus, he taste anus in Hindi. The main purpose of this test is to check the dielectric strength of the oil. Essentially, we want to see how well the oil can resist electrical breakdown. To perform this test, we use a BDV test kit, which is specifically designed for this purpose. The procedure involves gradually increasing the voltage applied to the oil sample until it breaks down. This step-by-step increase helps us determine the point at which the oil can no longer withstand the electrical stress. Now, the ideal value we're looking for is typically 60 kV or higher, especially for new oil. If the oil's dielectric strength is below this, it could indicate contamination or degradation, which might affect the insulation performance. Connecting this to our overall maintenance and diagnostics theme, This test is crucial because it helps us ensure the oil's quality and the reliability of the equipment. Regular testing allows us to catch issues early and maintain optimal performance. Now let's move on to the tan delta test, or He-Anus, He-Deltanus, He-Ace-Anus. This test is crucial because it helps us measure the insulation quality of the transformer. Essentially, we're checking how well the insulating material is performing and whether it's still in good condition. To perform this test, we use a tan delta kit, which could be from brands like Omicron or Megger. These are specialized instruments designed for accurate measurement. The key point here is the ideal value we want to see, which is less than or equal to 0.005 for a new transformer. This low value indicates that the insulation is in excellent condition, ensuring safe and reliable operation. Overall, the tan delta test is an essential diagnostic tool in transformer maintenance, helping us predict potential failures and plan timely interventions. Remember, maintaining good insulation quality is vital for the longevity and efficiency of our transformers. Let's talk about the high voltage test, or He-Anus, He-Wall-Nus, He-Ace-Nus. The main purpose of this test is to verify the insulation's withstand capability, ensuring that the transformer can operate safely under high voltage conditions. To perform this test, we use an HV test set, which provides the necessary high voltage. The procedure involves applying the specified voltage for 60 seconds, following the standards outlined in IEC 60076. For example, if we have an 11 kV winding, we apply around 28 kV AC, and for a 33 kV winding, it's roughly 70 kV AC. The goal here is to check that there's no breakdown or insulation failure during this period. The key point to remember is that if the insulation withstands this voltage without any breakdown, it confirms that the transformer can handle the electrical stresses during operation. This is a crucial step in ensuring the reliability and safety of the transformer before it goes into service. Let's take a closer look at the summary table, which outlines the key test parameters and the ideal values we aim for during equipment testing. Starting with the IR test, we use a Megger to ensure the insulation resistance is at least 100 megaohms at 11 kilovolts. This is crucial because good insulation resistance indicates minimal leakage current and reliable operation. Moving on to the power factor or pi test, again with a Megger, the ideal value is 2 or less. Maintaining a low pi value signifies healthy insulation with minimal degradation. The TTR test, which measures the transformer turns ratio, should be within plus or minus 0.5%. This ensures the transformer is functioning properly and that the ratio is within acceptable limits for optimal performance. For resistance testing, a micro-ohm meter is used, and the difference should be less than or equal to 2%. This helps us identify any abnormal resistance that could lead to overheating or failure. Next, the vector group check, performed with a meter, should match the specifications on the nameplate. This confirms the correct phase connection and vector orientation crucial for system compatibility. During no-load testing with a wattmeter, a reading of 1 to 3% indicates the core losses are within acceptable limits, reflecting efficient operation without load. For short-circuit testing, the wattmeter should show %Z as specified on the nameplate, which helps verify the impedance characteristics of the transformer. The oil BDV test, using a BDV kit, should measure 60 kilovolts or higher, indicating the oil's dielectric strength is sufficient for insulation. Tan delta testing, which assesses the dielectric loss, should be less than or equal to 0.005, confirming good insulation quality with minimal losses. Finally, the high voltage test with an HV set must show no breakdown, ensuring the equipment can withstand the specified voltage without failure. All these tests and their ideal values are essential in ensuring the reliability, safety, and efficiency of electrical equipment. They serve as a comprehensive check before commissioning or after maintenance, aligning with our overall goal of maintaining high standards of electrical safety and performance. Thank you all for being here today. I truly appreciate your time and attention. I hope the information I shared has been insightful and helpful. I would like to take this opportunity to thank everyone who contributed to making this presentation possible. It's been a pleasure to present to you all. Presented by Varun Vijay. Electrical Department. Once again, thank you so much for your interest and engagement. If you have any questions or want to discuss further, please feel free to reach out. I look forward to working with you all in the future. Thank you.